In this video lecture, we'll talk about convergence of random variables. The first thing to note about convergence of random variables is that since random variables are Borel functions from a probability space to the real line, we can translate all the previous definitions of the previous video lecture of convergence in terms of probability spaces. So now we change the notation as well as usual. So the function which is defined on a probability space, we denote it by capital X instead of lowercase f. And the measure mu now is a probability p. So instead of almost everywhere, we say almost surely. So it's the very same definition that we had before, just now dressed differently. So we say that random variables xn, a sequence of random variables, converges almost surely to another random variable x if, well, the set of omega for which this limit holds has probability 1, which means, of course, the set of omega for which this limit does not hold has probability 0. So this is really just the same concept we had before with new notation and terminology. And likewise, for convergence in measure, we now call it convergence in probability. It's still correct to say almost everywhere here if we want, and convergence in measure here if we want. But this terminology, it is helpful because it tells us that we are on a probability space and these Borel functions are to be understood as being random variables. So, and of course, now we write p here instead of mu if p is denoting the underlying probability measure in whatever probability space where these variables are defined. And the definition is the same. The measure of the set of omega for which this difference is larger than epsilon, it tends to 0 for every positive epsilon. And like before, we can denote this space LP. LP is a vector space. It depends on what is the measure P that we put on the measurable space. And it converges in LP or in P's moment. That's the language more used in statistics. And it's denoted like this. So fxn tends to x when n tends to infinity in this space LP. So this is when n tends to infinity. It means we say that if x is in LP, okay, which means the expectation of absolute value of x to the power p is finite, and it means this integral, which is now we call expectation instead of integral, the integral of this difference between xn and p, and xn and x, absolute value to the power p, it converges to 0. Now here's a remark which holds on probability spaces, but not necessarily on other measure spaces, because probability spaces are finite measure spaces, which is if a sequence of random variables converge in LP, then the average of these random variables, it is defined, and it also converges to the average or expectation of this limiting random variable. And the proof of this is actually quite simple. So what we want to show that this sequence, we want to show that this sequence here converges to this random variable, so to this number. So this claim here is about a sequence of numbers converging to another number. So let's restate this as the difference, this difference tends to 0. And the difference tending to 0, we can just as well say the absolute value of the difference tends to 0, and it doesn't hurt to raise it to some power p. So let's do this just for convenience. So I'm writing it here, and that's what we want to show. We want to show that this tends to 0, but now here we can use the fact that the expectation is linear. So we have this becomes the expectation of xn minus x. And here we can use Jensen's inequality because of taking, no, here we can use the inequality that the expectation of z is less than the expectation of z. This is what we are using here. And finally, we can here use Jensen's inequality from here to here, from this. So this is Jensen's inequality. So raising it to the power p, okay, this is a convex function, and here we are using p, that p is at least 1, otherwise it would not have been a convex function. Yeah? What's the convex function? Phi of t equal t to the p for t non-negative. This is a convex function. We can see that by computing the second derivative, show that phi prime prime is non-negative, so it is convex. So now we can say the phi of the expectation of xn minus x, which is what is written here, is bounded from above by the expectation of phi of xn minus x. And what is phi? Phi is to the power p. So this term here is really the same as this one, and this term here really is the same as this one, which justifies this inequality. And this tends to 0. Why does it tend to 0? Well, that's the assumption. We're assuming xn tends to x, and this is the definition of xn converge to x in LP, is this expectation converging to 0. So this proves the remark that convergence in LP implies convergence of the mean.